Okay, good evening, everyone. I am Anuradha Vijayasinghe. I am the Secretary of Institute of IESL WA chapter. So welcome. This is our first presentation for 2021. So please forgive us if we have any missteps along the way. This presentation is organized by our Mechanical Engineering Subcommittee group. So before I go on to introduce our presenter tonight, I would like to go through some basic online etiquette and the general format of this evening's presentation. Etiquette-wise, quite simple. Please keep your microphones on mute. I think already everybody is put on mute. You will get an opportunity to ask questions at the end of the presentation. But having said that, the presentation will be about 45 minutes to 1 hour. But during the presentation, feel free to type in questions in the chat box. So what I can do is, as the presentation is going along, and if there's a general pause in the presentation, I can ask our presenter those questions. If I don't get through all the questions, we can always do it at the end of the session as well. So I think, yes, that's about it. So I would now like to invite Engineer Tissa Vijayasinghe, who is the president of the WA chapter, to introduce our presenter. Thank you.
Thank you, Anuradha. Hello, ladies and gentlemen. It's an honor, Professor. Professor Tilak Chandatilaka, he is an old student of Ananda College, Colombo, and Faculty of Engineering, University of Sri Lanka, Peradeniya campus, from which he has obtained his mechanical engineering degree. And his specialization is in boiling heat transfer. He has obtained his PhD from Cambridge University in the United Kingdom. And prior to joining the academia, Professor Chandatilaka has worked in the industry as a consulting engineer in the UK and USA, which means he is bringing his industry experience to the classroom. His research is wide-ranging, spans across heat transfer and fluid flow industry applications. These include fundamental and applied discoveries in microlayer theory in boiling, pulse jet electronic cooling, microchannel flows, microfluids, fluid flow through curved passages, which is the topic of this presentation, and of course, patents for commercial thermal product development. Coming on to academia, he has significantly contributed to the development of mechanical engineering university programs in Singapore, Australia, Malaysia, and Sri Lanka. He serves on the editorial board of the Institution of Mechanical Engineers UK and is currently the national chair of the Australasian Fluid and Thermal Engineering Society of Engineers Australia. For several years, he has acted as an executive member of the Engineers Australia Mechanical Branch in Western Australia and expert college member of the Australian Research Council. Currently, he is the head of mechanical engineering discipline at Curtin University in Perth. So without much ado, I would like to hand over to Professor Tilak Chandatilaka. And thank you, Professor, for accepting this offer. Over to you, Professor.
Okay, thank you very much, Tissa, and also Anuradha. And it's certainly a very big privilege, to be able to do this first presentation particularly. And I'm very pleased to be a part of this IESL programs. And being a Sri Lankan, it gives me so much of proud feeling as well to be able to contribute in this manner. And I like to thank Ashok as well, who initially invited me to do this presentation, which is I know Ashoka, so I think that was the connection established in that way. Anyway, I can recognize so many names, whom I have studied with in the past, and also I can see my son is one of the members participating as well, and my father-in-law as well. So, so quite a collection of different kind of a spectrum of people actually in this presentation, which makes it very difficult for me to talk at the normal level I talk, because I have to make sure I deliver at the right level so that people understand. But having said that, I'll make the presentation very, very general. But of course, I have to talk in my language, which is the mechanical engineering, heat transfer, and fluid mechanics kind of a jargon as well. But I'll try and keep it as simple as I can. But it's inevitable. There are certain elements which I have to bring in to explain certain things. So please put up with me. If you don't understand something, you can always give a better explanation a bit later. Anyway, this presentation essentially about my almost 25 years of my research and cramped into this 45 minutes to 1 hour. It's a very difficult kind of a task. So I have chosen very key elements of what I have done in the past and try and give you the flavor of my contributions and my discoveries kind of things. And through that, I'm expecting to have a better appreciation for the part of the research I'm doing, which involves curved passages, the flow through curved passages, sometimes what's happening in the nature as well. So in terms of technology, there are certain things I'm going to talk about. In terms of nature, I'll be talking about certain things as well. So it's quite a range of things I will be bringing in for the discussion today. And I hope it will be very, very appealing to you. And as I said, I can always clarify if there's any doubt in your understanding or following the discussion. So let me go back to my PowerPoint presentation. So the title of my presentation is Fluid Structures and Thermal Behavior in Curved Flow Passages. This is very simply, it says we are looking at curved passages and we are looking at fluid structures within that passage, and also it brings in certain kind of a flow behavior. Normally the passages, the fluid flow passages are used to transfer heat or extract heat from a particular device. So that is the main thrust in this particular work or presentation. Now, before I go into the actual details, I like to acknowledge my co-workers for over the last maybe 20 years or 15 years, and Nima Nadeem, Ramesh Narayanaswamy, and a numerous number of PhD students who have gone through my type of research and produced outcomes which I'm going to actually present to you. It's not just my effort. It involves a big team of people actually in the past from time to time. Now this particular observation of flow through curved passages was initially came through one of the very very simple day-to-day kind of a experience. Now, if you have a cup of tea, like what I have shown here, and when you start stirring that cup of tea, you will find that the tea leaves actually get into the center, not to the edges in the teacup. Now, obviously, these days we have tea bags, so we don't have that tea leaf issue. But in the past, we always had loose tea bags, loose tea leaves. So when you start boiling water with the tea leaves, and then you have some leftover tea leaves with that. So when you start stirring this teacup, you find that the leaves actually don't go to the edges, they come to the center. Now, this was quite puzzling. Obviously, at that time, there have been many probing kind of minds in the society. They were looking at why this is happening actually. We expect the tea leaves to go to the sides, but it doesn't go to the sides, it comes to the center. So this question was presented to Einstein at one stage, and it's called the tea leaf paradox, which was actually solved by Einstein. Now, in this particular process, what's happening here is essentially when you have a rotation like this, when you start rotating a fluid like this, you find obviously it's the centrifugal forces. The centrifugal forces are the ones that you observe or you feel when you are taking a turn in a car or a train or some other vehicle. You feel that somebody is being pushed to one side. So that's a centrifugal effect. Now this centrifugal effect actually creates a loop of circulation like this. Now obviously we are turning the fluid in that manner in the vertical, along the vertical axis, but the circulation of water happens within that, in that manner, perpendicular to the direction of the rotation. Now that happens due to the pressure gradient that you have between outside and the center. Now that particular motion is always perpendicular to the direction of the rotation. So this is why the tea leaves come to the center and try to remain there. Even while you are stirring, it remains almost stationary within the center. Now this is actually a very clear separation process. Now if you want to separate the tea leaves from the liquid tea, now you can apply this kind of process. Now this is actually being used by many technological devices in the past, and even in blood test or blood test kind of situation, you want to separate the blood cells from plasma. So you have a rotational device, the magnetic kind of rotation. Now through that rotation, you can actually separate red blood cells, which are heavier than the plasma, to the center. And also there are cyclonic vacuum cleaners, modern vacuum cleaners, and certain separators in cement industry, or dust separators, the grain separators. You can use the same technique. And the bladeless fans. Nowadays we have bladeless fans and hair dryers. I can't mention the brand, but you can easily guess what it is. So these bladeless fans also operate in the same principle. Or when you go to the toilet, you will see that hand dryers, which you put the hands into it and it works automatically. Now that kind of hand dryers operate in the same principle. And in nature, we have this atmospheric pressure systems, tornadoes kind of things. Now that again have the similar kind of behavior. We have a rotational fluid mass, and then you have another rotation perpendicular to that particular motion. So this is the clear motivation to do this kind of a work in research. Now I undertook this kind of a challenge, and you might ask the question, what is the common thing between what I just mentioned to you versus curved ducts, which I've been looking at? Now obviously there's a connection. Now the connection is through the unique fluid structures or mechanisms that you find in flow through curved passages. Now that's what I'm going to talk about. Now here I have a very simple schematic of a curved channel. This is the curved channel, and the fluid is flowing in that direction. And like when you're traveling in a car, as the car takes a turn, people get pushed to the outside, sort of outside of the car to some extent. Now that same thing happens here. When the fluid is flowing through this pipe or passage, the fluid is being pushed in that direction, in this direction of the arrow. And if I'm looking at a cross section here, this cross section here, rectangular or circular cross section, you will find the fluid is actually going to move towards the outer boundary. This is the outer boundary, that's the outer boundary, and that's the inner boundary, and that's the inner boundary. So this particular fluid motion creates some kind of circulatory fluid motion within the channel. Now this behavior is clearly the uniqueness or very unique behavior in curved passages. Now the circulatory flow of this kind of circulatory flow is going to be superimposed on the flow through the channel itself. So what happens now, the flow is going through the channel as an axial flow, and then you have this circulatory motion superimposed on the channel itself, on the flow itself. So it gives you some kind of a spiral kind of a fluid motion to the axial fluid. Now that is not commonly found in any other pipe systems, any other geometry. You don't find that kind of thing, because in a straight pipe, you have the fluid flowing directly through the pipe itself. It doesn't have the circulatory spiraling kind of motion. Whereas when the fluid is going through a curved passage, you have that spiraling fluid motion. Now this fluid motion is what we mean by the secondary flow, or we call that secondary vortices. So what's shown in red here are the secondary vortices. Now they operate in opposite directions. You can see this is clockwise and that's counterclockwise. So that's the typical behavior of secondary flow. Secondary flow always behaves as a pair of vortices. Now what happens? It's not the end of the story. Now we can actually look at some other thing as well. Now when the centrifugal force is in action, it also creates what's known as adverse pressure gradient. Now, adverse means the pressure gradient developed by the fluid is going to be against the fluid motion. Now you can see here, the fluid is flowing in that direction of the arrow, but the pressure gradient will be increasing in the same direction like that. Now that is not the normal fluid behavior. Normally the fluid flows when there's a pressure gradient, but the pressure has to drop from inlet to outlet. So here we call that an adverse pressure gradient. Adverse means it's against the fluid motion. Now when this kind of flow happens, the fluid gets slowed down, obviously. The fluid gets slowed down when it reaches the boundary here, and also when it reaches that boundary here. And then when you keep increasing the flow rate, you find at particular point of the flow rate, the flow is going to be reversed at that point, because it can't remain at that point when the pressure is higher here compared to the pressure on the other side. So the outer wall actually reverses the flow, and it creates another pair of vortices at the boundary, at the outer boundary. Now those additional vortices are called Dean vortices. It's named after the people, the scientists who discovered this particular phenomenon called W.R. Dean. And this phenomenon of appearing of Dean vortices is called the Dean's instability. So that term I'll be using all the time. Now, as you can imagine, this Dean's instability happens at a particular velocity. It doesn't happen below a particular velocity because the velocity is not strong enough to create this pressure gradient. But when you increase the pressure gradient, you find the Dean vortices will kickstart, and that happens at a particular velocity. So there's a critical velocity beyond which the Dean vortices will begin to appear in this kind of a curved passages. Now that is of great interest to the research as well as various design processes. So I'm going to talk about some of those things a bit later. Now, what is more important here to be able to recognize, when you have this kind of a flow in a curved passage, it has a characteristic difference compared to the straight passage. It improves fluid mixing because we have two pairs of different types of vortices here. We have the main secondary vortices, and also we have the smaller Dean vortices. Now they begin to actually churn out the fluid much more rapidly inside that passage, and then it creates a mixing process. Now that is very useful technique for various drug or medicine kind of applications, aeration kind of applications. We need a lot of mixing in the fluid. So that is what we can easily achieve by having this kind of a geometry. But more importantly, it has a unique ability, to enhance heat transfer as well. Now that is of great interest to me because being a heat transfer person, I like to have a look at the ways to improve the heat transfer process. So here I have an option, even without doing anything, just by having a curved passage, I'm able to actually increase the heat transfer rate compared to a straight passage. Now that's a very appealing kind of a strategy. All you have to do is have a curved section in a passage, it will improve the heat transfer. So how much it improves? Now that is part of my research for the last 20 years or 28 years kind of a thing. So this has two major effects. One, of course, it improves mixing in the fluid, and also it has an intrinsic ability, built-in ability to enhance the thermal process in that channel. Now later you will see how we can enhance or harness this particular mechanism in thermal designs and so on. So thermal enhancement wise, you will see that there are many opportunities available. If you take a normal heat exchanger, the fluid will go through a curved section. Invariably, you have a U-turn kind of a thing, or you can have the baffle kind of flow like that. Now, in all those places, you'll see that the secondary flow will be in action. You don't see it, but it's happening in there. And similarly, you can have special geometries for heat exchangers. This is one of the geometries which I have developed previously. It's called the spiral coil heat exchanger, SCHE. Now, this is simply a coil which has a varying radius of curvature. You can see initially it's large curvature and it becomes narrower and narrower and comes here. So unlike the work I have explained to you before, with the constant radius of curvature, now this particular device will have a varying radius of curvature. So that behaves quite differently to the previous case. But this is one of the options available. But the main interesting thing here, it's very, very compact. You can see the geometry of this. It's circular and it can remain within a very, very short dimension. And if you stretch this tube over a long distance, it's much, much longer and you cannot actually make it compact in that manner. But here we have an option to make it very, very compact. And that's a big appeal for certain applications like heat recovery from very low temperature systems. And then you can use this kind of devices for refrigeration, chiller coils or air conditioning ducts. We can use that. And I have numerous projects which I have attempted before in this kind of areas as well. And then thermal enhancement can be extended to much more advanced systems. Turbine blade cooling is one of the options. Now here the turbine blades have a curvature. Obviously you have to have a curvature in turbine blades. Now as the fluid flows over the turbine blade, you will find that the cooling mechanism or heating mechanism is much improved due to this curvature effect as well. So that's another interesting option. And then when you look at even more advanced options, rocket engines. The engine of a rocket nozzle has a geometry like this. It has a high temperature combustion chamber up here, and the hot gases are pushed through the nozzle into the atmosphere. And that section here is what we call the throat. The throat is a narrower section of that nozzle, and that has the highest temperature, highest velocity, and so on. Now that section got to be kept very cool. Otherwise, the rocket is not going to work. It will break at that point. So we have this curved passage supplying coolant to go through that particular point, and there's a curvature here, and you can see the cooling channels around that nozzle, and that creates a very high heat transfer rates at that particular nozzle or throat, and therefore you can keep the nozzle, the rocket engine nozzle, very, very cool. I mean, this is the typical technique used in this kind of devices. And then closer to home, we have more interesting applications like modern vacuum cleaners. You have this kind of a cyclonic separators in modern vacuum cleaners. You feed the mixture of, say, dust and air into that cyclone, and then it sets up a rotational or cyclonic motion, and that motion separates solids out of the system, and then the clean air can actually leave through a different path. So that is what you mean by cyclonic separation. So with that particular device, you can make vacuum cleaners without a bag kind of a thing. You can separate the solids. You can even have grain separators, the husk from the grain. For instance, a rice husk can be separated from rice. And then also you can separate cement particles from air kind of a thing. All this can be done with this particular technique. This involves the secondary flow. You don't see that from outside, but that's a mechanism behind that. And then in nature, we also find this kind of a thing very, very easily. If you look at a tornado, the tornado actually has a very circulatory motion set up by the temperature differences in the atmosphere. Now that sets up the vertical motion. You can see the air mass around the tornado rotates in a circulatory manner, but the actual motion is vertically through that eye of the tornado. Now that's where the destruction is, because this is a very high speed kind of a draft coming through the center. Now that is the most destructive part. Now that's what you see in this picture. You can see the tornado pulling out the debris from the ground. Even the houses, cars, and other things can be pulled with sufficient suction power in the cyclone. So that's again very much a secondary flow effect. Now, another application, very interesting application, is the riverbank erosion and sedimentation. Now here we have a river going through a bend. River takes a bend, and then the water, whatever the soil around the outer boundary here is picked up by the secondary vortices and dumped inside the inner boundary. You can see the inner boundary getting filled, the outer boundary gets eroded in this kind of situations. And this picture shows the sedimentation happening here and the erosion happening here. So this is again very much a secondary flow effect, and that's one of the research areas that I have examined as well in my latest research. So what are the key things developed over the years? Now, very first incident of secondary flow scientifically observed and experimentally observed in 1911. It dates back to 1911, very, very long time ago, almost how many, 110 years ago, by a person called Eustace. And then later on, W.R. Dean, you remember the name now, Dean, the Dean vortices, and he related the secondary flow to a particular non-dimensional number. Now, you might wonder what this non-dimensional number is. I think those who have done engineering remembers non-dimensional. It has no units, essentially. So it's the same parameter divided by similar parameter with the same units. So when you divide one unit by the other, the units cancel out, it becomes dimensionless. It's what you call the dimensionless number or non-dimensional number. Now, normally in fluid mechanics, we use Reynolds number as a dimensionless number. But in curved passages, we cannot do that. We have to have a different number. Now, that's what the Dean identified. Dean identified a special number called Dean number, which is defined in this manner. Don't worry about why this is defined that way. I just want to show you the structure, and later I'm going to use that notation all the time in my discussion. Now, this is the radius of curvature, or the diameter of the passage, and that's, sorry, this is the diameter of the passage itself, and that's the radius of curvature. And then this is the traditional Reynolds number, which defines the fluid flow. So you can see the Reynolds number has been modified by the curvature ratio. This is a DOH is what we call the curvature ratio to the power half. And then we have the Dean number, which is the notation we use to identify Dean number. So every time you see capital K, we use, we know it's a Dean number being referred to here, especially in curved passages. Now, the Dean number identifies that critical condition which requires to develop Dean vortices. So Dean vortices are developed in relation to critical Dean number. So we have a nice parameter which identifies when the Dean vortices are going to appear in a passage. Now, that's a very, very powerful contribution to this particular field, because without that, we are guessing so many things. We don't know exactly when it's going to happen. At lower flow rates, it doesn't happen. At higher flow rates, suddenly the Dean vortices appear. Now, that transition from no Dean vortices to Dean vortices is determined by or identified by this particular number called the Dean number, which is a very, very nice thing to have. And then subsequently, many researchers went on to develop various things, various ideas through their research. Moffat, Bayliss, Humphrey, they are some of the key names at that time in this particular field. And then there was another major contribution to this particular field by Cheng, whom I have worked with some time ago, and then Sugiyama, a Japanese researcher, and they actually looked at the Dean instability much more closely, and they identified the Dean number itself is not good enough to identify the instability or the Dean number, the Dean vortex appearance, and they mentioned that they identified that even the geometry has a role in that, and the curvature definitely has a role in that. Lower the curvature, the higher the effect of this particular effect as well. So later you will see some of these effects. Now, the most important thing here, Cheng et al. And Sugiyama, they developed this particular, what we call a phase diagram. It's something like a a diagram which identifies the boundary of the Dean vortices in the system, not in the system. So that boundary is defined by this particular line. So that line actually identifies when the Dean vortices are going to appear for the first time. Now, suppose we have a channel with aspect ratio 4. Aspect ratio means the height to width ratio in a rectangular passage. If you have a circular passage, aspect ratio is 1. So here we have a, say, B to A over ratio, say at 4. And if you work along this line, when the Dean number is lower than this particular value here, there's no Dean vortices in the system. And when you go past that, all of a sudden Dean vortices appear. So this is a very, very important observation the Cheng et al. And also Sugiyama et al. Identified in this particular field. Now this kick-started enormous interest in this particular field. And that's how I got interested in this particular field as well. So the critical Dean number, sorry, yes?
There is a question that came from, it's about the Dean vortices. Shall I put it to you?
Yes, yes.
It's from Nalin Vikramanayaka. Are the Dean vortices and the critical Dean number relevant only for laminar flow?
No, absolutely not. See, when you have laminar flow, you don't have the normal disturbance created by turbulence effects. So because of that, you can actually see the Dean vortices much more clearly in laminar flow, but it doesn't restrict the Dean vortices only to the laminar flow. We have seen even in turbulent flows, like in rocket engine nozzles, for instance, you can have Dean vortices appearing as well. But you have to go past that critical point. There's some notation, some request appeared here. Somebody's asking to control your screen. Do you want to decline that? They're asking whether I should approve it or not. Maybe I will decline. I'll decline that.
Yeah, I'm not sure who did that.
Yeah. Anyway, now this critical Dean number obviously identifies the onset of Dean vortices and Dean's instability. And also it, I got the same request again. And then it also have a very special thing. When you can see here, this particular curve flattens out as we go towards higher aspect ratios. Now, what it means that you need lesser flow rate or lesser Dean number to activate the Dean vortices in the channel in that manner. Okay, so that's one of the observations you can see. So now, having gone through that previous developments, then my name keeps appearing in this particular field, because since 1998 up to now, I have made some important contributions to this particular field, and especially I have developed numerical models in 2-dimensional, 3-dimensional numerical models to describe this kind of a secondary flow and onset of Dean vortices. And we looked at many geometrical arrangements, rectangular passages, square passages, elliptical, and circular passages as well. And we looked at single phase, two phase. Two phase means you have two different types of fluids, or fluid and a solid, or fluid and a gas flowing together as well. And then you can also have the granular or slurry flows in the system as well. So we looked at so many different things. Obviously, we didn't do this at once. It's a gradual development since, say, 1995 or a little bit later than that. We have been looking at ways to improve our research knowledge, and we gradually looked at different scenarios through the PhDs and so on. And some of the key outcomes, recognized outcomes, are listed here. Now, obviously, we have to identify the Dean vortices. We can do the numerical modeling or experimentation, but we have to have a technique by which we identify the Dean's instability, vortex detection. And nobody has developed this technique. And through my research, we developed two different techniques to identify when the Dean vortices would appear in the passage. Without doing anything, we can actually identify that very clearly through a particular technique. I will talk about that a bit later. And also we used secondary flow to optimize the thermal behavior of passages. using entropy. Again, I apologize if somebody doesn't know the word entropy. Entropy identifies what we call the irreversibility in systems, in processes. That means when you do some process, you cannot get back to the original state, because we have a natural direction in a process. It's like water flowing from high elevation to low elevation. To pump it back to the high elevation, we have to have additional energy pumped into that. So that kind of a one directional flow systems are identified by entropy. So using that technique, we were able to optimize thermal behavior of certain passages as well. And then we have extended the research or observations in secondary flow to two-phase systems, which people haven't done before, and non-mixing fluids, something like oil and water flowing together, or air and water flowing together, and also boiling systems. That means we have steam and water flowing together as well. So we've looked at the entire range of possible combinations of fluid systems as well through the passages. And then we have looked at the channel bed erosion. When you have open channel or closed channel with a particle bed, and how the bed is going to behave in the presence of this kind of a vortices, and then how the sedimentation is going to happen in this. All these have been published in literature, and you can have a look at it. And also we have developed a very compact novel heat exchanger configuration. You saw one of them, the spiral coil heat exchanger. And I have currently one student actually working on this particular thing as well. We are using a different technique, not the previous techniques we used in our previous work. We are using a completely different frequency spectrum kind of analysis is being used at the moment. So that's the kind of a contribution I have made over the years to this field. Now, initially we did fairly elementary experiments. We simply have a curved passage like shown here, two passages communicated through this kind of a wall, heat transfer wall, and one fluid is hot, the other fluid is cold, and there's a curvature in the passage. And then we looked at thermal behavior, how this particular heat exchange is going to behave, and then we compared that with the equivalent straight heat exchanger as well. And then we compared the two, and we noticed that there's a significant improvement in heat transfer performance in that particular heat exchanger. So we can achieve something like 17 to 23% better thermal effectiveness in curved heat exchangers compared to a straight heat exchanger. And then we went on to look at the spiral coil heat exchanger, which has a varying radius of curvature, of course. And then you can see this kind of a layer in here, and you can have multiple layers like this so that it can handle large amount of volume of fluid passing through as well. So we did a lot of testing on this kind of a thing. And again, we noticed a significant improvement in thermal performance. We have 20 to 30% kind of a thermal performance, thermal effectiveness, in addition to the compact nature of this kind of a heat exchanger compared to a straight heat exchanger. If you take this particular spiral coil heat exchanger and make it very long, you can imagine the dimension of that particular heat exchanger. It's going to be a very, very long heat exchanger. It will not have the same effect as the spiral coil. So that's a huge advantage in this kind of a situation. So that's one of the major things we have done as well. Now, when you're doing this kind of numerical work, obviously the mathematics tend to be extremely complex. Even without the two phases, with a single phase, it is very complex because we have a centrifugal action, we have the motion, which is the fluid motion, which is already complicated. We have the continuity equation, we have the momentum equation, then we have the thermal equation on top of that, when you have heated walls and so on. And also we have centrifugal kind of a body force terms. You may not be familiar with some of these terms, but don't worry about them. This is simply the centrifugal action introduced into the flow. And then we have to look at Navier-Stokes, continuity, and energy equation. You can see the complexity in these equations. So now to solve this on its own with the primary variables, it's an extremely difficult thing. We cannot do that. So we had to introduce something called the helicity. The helicity is like a corkscrew. When you have a rotation the corkscrew identifies the intensity of that particular rotation. So that's what we use. The H is the helicity, and we convert that in non-dimensional term like this. It's a non-dimensional helicity, and then of course we looked at the heat transfer as well. So we looked at this kind of modeling with the heating applied to the inner wall. This is the inner wall of the passage, and also we applied the heating to the outer wall of the passage, inner wall, outer wall of the passage. So we can look at different cross sections, rectangular, elliptical, circular, and square ducts. You can have any shape of duct, and then we can also look at with and without wall heating, inner wall heating or outer wall heating. So we looked at so many of these different combinations. And just to give you an idea of the type of parametric range we have been looking at, we looked at laminar flow, turbulent flows. I think some of you are familiar with these terms. And the temperature dependent properties we looked at. When you have heated fluids going through the passage, obviously the density will change, the viscosity will change, thermal conductivity will change. Then we have to accommodate all that. And the early models ignored all these things because they want to simplify the problem as much as we can. So here we took everything into account, and then also we looked at enormous range of the Dean number, going from 80 to something like 1600 value. And wall heat flux again, very high, 1000 watts per square meter. I mean, these are extreme values, if you like. So we looked at full range of work like this, and then we applied the same modeling, of course, with certain modifications, to two-phase as well as single-phase immiscible. That means non-mixing fluids, the mixing fluids, the boiling fluids with the phase change. That means the boiling fluids will have even more complications because you have the vapor condensing or liquid evaporating. So that has a mass transfer on top of the normal heat transfer as well. So you can see the complexity gradually building up over the years in our research. So we applied all these techniques, and then we managed to come up with some sorry. So I'm going to show you now a certain animation which will help you to understand the development of these vortices or the secondary flow through the passage. Now here we have a passage, and you'll see a marker going across that later, indicating the position at which these helicity contours are illustrated. So here we have a non-wall heating situation. There's no heating in this particular case. And then on the right-hand side, you have the wall heating case, which I will show you later. And this boundary is called the outer wall, and that boundary called the inner wall. So we have the outer wall, inner wall in all of them. So let's see how the animation happens. Hopefully it will happen. So you can see the secondary vortices are developing slowly as the position of the channel changes. We are looking at different cross sections here, and for each cross section, we can predict how the vortices or the flow patterns going to develop through that passage. So you can see the Dean vortices appearing here at that wall, and these are the main secondary vortices. The big ones are the main secondary vortices, and then it gets pushed by the Dean vortices appearing at the outer wall, always appearing at the outer wall. Initially, you have only the main secondary vortices, and then you have the onset of Dean vortices inside. Okay, and then this is a different shape, elliptical shape, of course, and it has a different geometry compared to the rectangular passage. We can look at different types of geometries in that respect. We can look at even the circular shapes, which we're going to see later on. Then I'm going to now move on to the next side with the wall heating. So with the wall heating, the difference is when you have wall heating applied to the inner wall. Inner wall is the right-hand side. The inner wall will create what you call a natural convection circulation, because the wall is heated and the density becomes lower at that particular point, and then you have this circulation happening like that, starting from the inner wall, and that's going to interact with the vortices, secondary vortices first, and then Dean vortices later as well. So you can see the geometry has changed. The structure of the vortices have changed because of the heating happening from one of the walls. You can have the same behavior with a slightly different geometry when you apply heating from inside as well. So later you will see this a bit more. I just want to give you a feel for the Dean vortices and secondary vortices appearing in the channel. This is coming from our simulations. So here I have several passages with an increment in Dean number. You can see the Dean number 20 and gradually increasing to something like 500 here. And this is our experimental observation. We use some kind of smoke to identify a particular cross section and how the Dean vortices look like or secondary vortices look like at that point. You can see the Dean vortices appearing here at the outer wall and the Dean vortices appearing here as well. And then the main secondary vortices are in here appearing. Now with a simulation, you can see that more clearly. You can see when the flow is lower, we have large secondary vortices in the passage up to about 300, between 260 and 300 Dean number. You'll see that only the main secondary vortices appear, and all of a sudden you have that the Dean vortices kick-starting from the outer wall, and then it becomes more intensified as we go towards higher flow rates. And then when you increase the aspect ratio, the height to width ratio, now this is the 4, aspect ratio 4. This top diagram is aspect ratio 4, and the bottom diagram is aspect ratio 8. The height is 8 times the width in this case. And you can see the same sort of a thing happens. You initially have the large secondary vortices, and then gradually you have the first appearance of the Dean vortices at the outer wall. And when you increase the flow rate a little bit more, you have additional pairs of Dean vortices. So Dean vortices are not limited to one pair only. It can have more than one pair. So here you can see there are 3 pairs appearing in this particular case. Now that's very characteristic. With aspect ratio of 8, you only have 8. Sorry, you only have 3. It always appears in multiple of odd numbers. The aspect ratio 4, you have only one pair of Dean vortices. Aspect ratio 8, you'll have 3. And if you go to aspect ratio 16, it becomes 5, and so on. So it has a certain pattern. The pattern is actually due to a certain principle in this kind of problems. It's called the bifurcation problem, which I'm not going to go into. But the main thing I want to show you here, with our analysis, we were able to predict the secondary flow development in a passage, and also we were able to compare that with the experimental results, and also we were able to predict the onset of Dean vortices very clearly. And then we were able to show how the Dean vortices are going to grow within that passage as we increase the Dean number or the flow rate through that passage. So we are very much in progress along these lines. And we also notice one important thing. With the high aspect ratios, we have more and more Dean vortices appearing in the passage. Now that is something people haven't seen before. Through our experiments, we showed that you can have more than one pair of Dean vortices in a passage. So these are very important observations in our field. And then with wall heating, this is the effect of wall heating. And we are looking at outer wall heating at the top here. Now when the outer wall is this right-hand side in this case. And the moment you start heating the wall, you will find that natural convection is initially dominant. You have a large loop of fluid flow like this happening. And then as you increase the flow rate, the centrifugal effects will gradually become more and more dominant. And then you have the secondary flow or secondary vortices developing from the bottom of the passage, suppressing the natural convection circulation. So that's what we see experimentally as well. And in this particular case, you see that there aren't any Dean vortices appearing in the passage. Now, if you keep increasing the flow rate, at some point, you can overcome the natural convection effect completely, and then centrifugal effect will take over, and then start producing the Dean vortices again as well. And then if you, with the inner wall heating, we apply the heating from the left-hand side now. And in that case, the circulation loop will be slightly different. It happens in the clockwise direction in this case. And then as the secondary flow becomes stronger, it begins to form from the top. Previously, secondary flow started from the bottom, but now it's going to start from the top. So we can make certain observations. The observations are, with increased flow rate, outer wall heating actually assists the upper vortex. You can see the natural convection loop in the same direction as the secondary flow here, secondary vortex here. So it assists both heating. The heating assists both the natural convection as well as the secondary flow loop as well. Now, opposite thing happens when you have the convection from the inner wall. So in that case, the inner wall will actually suppress the upper one, and then gradually the natural convection becomes less and less because of the suppression. But in this case, we didn't notice any Dean vortices appearing in the system at all. Whereas in the outer wall heating, we could achieve Dean vortices a bit later in the flow with higher flow rates. But here, with the inner wall heating, you have a difficulty in getting the Dean vortices even with very high flow rates because of the direction of the natural convection loop happening there. So for that reason, we notice one important thing, that is, we can always achieve high heat transfer rates with outer wall heating than with inner wall heating. So that is one of the clear observations we came out of, or clear conclusions we obtained from this particular work. Now, this is the same sort of a pattern for elliptical shapes. You can see the shape is slightly different compared to the rectangular ones. And this is the circular shape. This is the first time you're seeing the circular shape. Now here in rectangular as well as elliptical shapes, the outer wall has the Dean vortices. The appearance of Dean vortices happens only at the outer wall. But in circular duct, it doesn't do that. Now that's the unique difference between circular kind of cross sections compared to rectangular or elliptical shapes. Now in circular ducts, the secondary flow happens as usual, like a big loop, which you can see in the very first picture here. And the Dean vortices will not happen at the outer boundary. It happens in the middle. It happens nearer to the outer boundary, and then it migrates slowly to the center. So that is a bit of a headache. It gave us a bit of a headache initially, because we developed certain techniques to identify these Dean vortices at the outer wall. But that system doesn't work for circular passages. So we have to come up with some other new technique. Now I'm going to talk about that in a minute. So that's a big difference between circular passages compared to elliptical and rectangular ducts in this case. Now, how do you detect Dean vortices? Now, that's a very important thing in this kind of a research. We got to know exactly when the Dean vortices are going to appear in the passage. Now, initially we thought only the outer wall will contribute to the production of Dean vortices. So we looked at the outer wall and looked at the pressure distribution along that line. We have a certain fluid pressure applied to this boundary, the outer boundary. We looked at how it varies. So we noticed that the fluid pressure goes up and down like this in a sort of a symmetrical manner between the two sides. And then when you increase the flow rate beyond a certain point, you suddenly find the gradient actually changes at that point. You can see the red circle here identifies the gradient is positive in pressure, and then gradually gradient becomes negative. And like that, we have another case like that here as well. So we looked at, maybe this is a very good way to identify the occurrence of Dean vortices. And that worked, beautifully worked throughout our experiments or numerical work with the rectangular passages, elliptical passages. There's no problem at all. Because what we did was we simply identified the positive to negative change in the pressure gradient along the outer wall. So that gives us a very, very nice way of identifying when the Dean vortices are going to appear in the passage. But unfortunately, it didn't work for circular passages. So we had to rake our brains or split our hairs to identify some other technique. Now that's exactly what we did in this new technique. Now this new technique is like defining the boundary layer thickness. I think those who have done fluid mechanics will know what I mean by boundary layer. The boundary layer is the viscous layer next to a solid surface when a fluid is flowing over that surface. Now there is a change in velocity from 0 to a particular value in the fluid through that boundary layer thickness. Now we can define the boundary layer by defining a certain sensitivity to the velocity change from the wall at 0 to the full velocity in the fluid itself. So we can do a similar thing here. We can actually define the helicity magnitude we can define as a parameter. So we define, say, 0.01 helicity, non-dimensional velocity 0.01, and that allows us to identify the Dean vortices with a certain precision. We can, of course, refine that precision by making it more and more smaller and smaller, so to speak. You can make, so for instance, 0.001 or 0.1. If you make it 0.1, the contours become coarser. 0.001, it becomes much finer. So that way we can identify and precisely locate the existence of the Dean vortices as a physical mechanism. So that gives us a very, very powerful technique. And we are the only people who actually develop this kind of technique in the world. So this is being used by everyone at the moment. So this particular technique is universally applied for any type of geometry, whether it's a rectangular geometry or elliptical geometry or circular geometry. You can apply this technique, whereas the pressure gradient technique only useful if the cross section is not circular. Otherwise, it doesn't work. Okay, so here we have a temperature gradient or temperature contours in flow passages, and you can see the stagnation kind of a behavior. The high temperature indicated by the temperature, red contours, and the blue indicates the cooler areas. So you can see the rectangular passage has a stagnant area at the top. In other words, the hot area at the top and cool area at the bottom. And hot area here, elliptical shape, cool area at the bottom in the elliptical shape. And this is with a lower flow rate, the Dean number 80. But if you increase the Dean number to 380, you can see the picture changes all of a sudden. The red areas disappear altogether, and the blue area becomes much more prominent in both rectangular passages as well as elliptical passages. Now, what does it mean? It means there's some kind of a transition happening from due to the dominance of the secondary flow effect, there's some kind of a transition happening from thermal effect to the viscous effect through that process. The blue means the thermal effect are less important. The red means thermal effect are more important. So there's a transition happening as we increase the flow rate or the Dean number from, say, lower value to higher value. Now that identifies a particular mechanism by which we can do thermal modeling or thermal optimization in passages. Now we notice one important thing here, that is the elliptical ducts are more affected by the wall heating and because of the shape. Now the shape supports the circulation due to the natural convection. Now when you heat this kind of this kind of elliptical shape on that outer boundary, you can see the shape itself supports the circulation in that passage. Whereas in a rectangular passage, you have these dead areas for the fluid. And that means the fluid will have to go through a little obstacle kind of a thing in that passage. So there's a difficulty in fluid to follow that path. Whereas in elliptical shape, it can follow the path. Now that has a certain significance, which I'm not going to explain all of that at the moment, but there is certain significance for this kind of a thing. Now, how do I optimize? We know the temperature profiles, but we cannot simply use that to optimize thermally. Now, to optimize thermally, we need to look at a different parameter called the Bejan number. Now, the Bejan number is developed by a famous scientist called Adrian Bejan, and I know him as well. I have worked with him on certain problems. Now, Bejan number identifies the thermal effect versus the total effect, total combined effect from the heating as well as frictional effects. Now, to do that, we had to define a bit more complex situation here. Now, that complexity comes from defining the Bejan number. I'm not sure whether you can see this because there are some pictures in here in the corner. The Bejan number essentially looking at the thermal or irreversibility in systems due to thermal effect divided by irreversibility due to thermal effect and frictional effect combined together. Okay, now so I'm not sure whether you can see it. The Bejan number is defined as ST. ST is the thermal effect, and you divide that ST is the thermal effect, and then SP is the frictional effect due to the fluid motion. So we add them together. We add ST and SP together, and then we have the total entropy change or total entropy behavior. And then we compare ST versus the total entropy in that particular system. So we look at mathematically, what we do is we take a very small fluid element here and look at how much thermal contribution is there and how much viscous contribution is there, and we add them together. And then we look at the ratio between thermal effect versus total effect. Now that these contours identify that Bejan number. So when the Bejan number is 1, it is completely red, like this. The whole space is filled with red. When the Bejan number is less than 1 or equal to 0, close to 0, the whole passage becomes blue. So you can see there's a transition happening in terms of Bejan number. Starting from red, it gradually goes through a transition all the way to blue. Whether it's a rectangular passage or elliptical passage, the same behavior you can see happening here. Now that allows us to actually optimize the thermal behavior without looking at many other things in these parameters. This is the only kind of analysis people have done in the world. We are the only people who have done this. This is again published very clearly, and it's a very highly cited kind of a publication that we have. So what it shows you here, when you increase the D number from 400 to say 1600, there's a gradual transition from thermal effect to viscous effects in the system. In other words, the thermal irreversibility becomes less and less, frictional irreversibility gradually becomes more and more. Okay, so that means we have an option of now optimizing the entire process. See where the minimum of these two combination lies as well. Now, if the system is blue, it's good for mixing of the fluid. When the system is red, it's good for thermal transfer. That means heat transfer is better when the system is red. System is providing better mixing when the system is blue. So that means we can actually do a optimization based on that. Now this transition, as you can see, is much more pronounced in the case of an elliptical shape compared to a rectangular shape. Rectangular shape, you can see even at 1600 D number, you still have some reminiscence of red left here, whereas the elliptical shape has become more blue compared to the rectangular shape. Now, because of this transition, we can actually do a nice optimization in thermal systems. How do I do that? Here I'm looking at rectangular duct, and I'm looking at all those ST, SP, and ST, S total combination, how they vary as we increase the D number, both for rectangular duct as well as elliptical duct. So the blue line indicates ST, and it keeps dropping like this as you increase the flow rate. And also in elliptical duct, it will drop, but at a different gradient here. The gradient is different. And then if you look at the black line, that's the SP, the frictional effect. It keeps increasing, more or less the same way in both types of ducts. And when you add them together, you will see that the total change, total irreversibility or total entropy value has a slightly different behavior. Now this has a minimum at some certain point, that has a minimum at that point. Now this minimum is higher than that minimum, which means the rectangular duct is going to behave better as a compromise between thermal effect and viscous effects compared to elliptical ducts. So that's what we have noticed. So we have a point of inflection which identifies the possible trade-off between the frictional effects and the thermal effects. The highest thermal effect or highest thermal benefit with the least friction is obtained at that inflection point. And it is good for rectangular duct, better than the elliptical duct. So that is the conclusion we came out of that. Now that's a very important observation as well. It identifies which shape would be better for certain applications. Now, based on our experience in these problems, up to this point, we have been looking at single phase fluids. So now we want to extend that to two phase fluids. That means mixing fluids, non-mixing fluids, and also various other solid and liquid kind of fluid flows as well. So this becomes much more complex now. And obviously the mathematical modeling becomes even more complex now. We have the fluid flow, we have the heat flow, and on top of that, we have two different phases going together at the same time. And then it becomes even more complex when you have a boiling kind of a situation, because you have the mass transfer happening. The vapor will condense or liquid will evaporate. So we have the heat transfer, mass transfer, the fluid flows, and then we have all the other usual fluid flow issues as well, turbulence effects, all kinds of things. And on top of that, we have another problem, that is the heat partitioning at the wall of the pipe. The pipe provides the heating for the fluid to boil, for instance, when in a boiling situation. So the way the heat is being transferred from the wall to the fluid is determined by many different mechanisms. You have the conduction, you have the convection, you have the evaporation, and then you have a drying out kind of a situation happening. Now, all these things we have to consider in developing a model like this. I'm not going to show that particular model to you. It may not make sense to you at the moment. It's very, very complex kind of thing. This is the highest level we have achieved in problems like this. Everything else is a little bit downhill kind of a situation for us in terms of mathematical complexity and so on. So this is a very complex problem now, much more than single phase. And we need to consider interaction across all the phases involved. Phase means different types of fluids flowing together or different substances flowing together. And then we have to consider heat and mass transfer interactions and also near wall thermal behavior, particularly in boiling. So these things make it very complex, and we took quite a while. And you can see how the different types of PhDs have been produced in this kind of a path. I have been working on different different groups of students and developing this one by one at different types of different times, at different capacities, and so on. Now here I'm showing you the helicity. We still use the helicity function. There's no problem with that. Now in here we have two different phases now. We have the heavy phase identified by red and the lighter phase identified by blue. So we purposely put the red phase or the heavy phase on the inner boundary of that passage. So you can see the inner section of the passage will have the red kind of a behavior, and the outside we have the blue behavior or lighter fluid, because we know that the heavy fluid is the one that's going to be responding to the curvature much more than the lighter fluid. So that's exactly what you see here. So when the fluid is going through the passage, now these numbers here at the bottom, 80, the theta equals 0, theta equals 45, 90, 135, and so on. Now those numbers identify, those angles identify the cross sections at different locations along that semicircular passage, if you like. So 90 degrees, sorry, 0 degrees is the beginning, 180 is the outlet. And in between, you have all these other cross sections. So you can see how the fluid, heavier fluid, is going to be pushed towards the outer boundary and then gradually comes back around the circumference to the middle again. And meanwhile, you have the complexity of Dean vortices appearing in the middle, as you see here. It looks very complex at the moment, And that's a square passage. Same thing happens. The heavier fluid is being pushed to the outer boundary and the Dean vortices appear like this. Now, it is not clearly illustrative here. I'm going to show you next operation in which we are looking at actual volumes of fluid for the heavy phase and the lighter phase identified by red and blue correspondingly, and how they behave through the passage. So again, at inlet, heavier fluid is on the left or inner wall, and the lighter fluid on the outer wall or right hand side. And then as we go through the passage, as the fluid flows through the passage, the heavier fluid is being pushed like a bullet through the center and going through a crowd. It's like somebody passing through the traffic kind of thing, and penetrating into the lighter fluid and then coming back to the center. Now this is again not very illustrative. If I show you the animation, you will see how it's going to happen nicely. So this is the animation again, showing the inner wall carrying the lighter fluid, heavier fluid, and the outer wall carrying the heavier fluid, both for circular passages and rectangular passages. And the location along that line indicates which cross section we are looking at in a particular instant in time. So let's see the animation. So you can see how the heavier fluid is going through that center part and then embracing the boundary and coming back to the center. Now, this kind of observations, we are the only people who have done this kind of work and published this kind of research up to now. So you can see how the predictions can be done in this manner. And we have done experimental work as well to identify this kind of behavior and conclude various operations in this way. And then the most advanced one, of course, the boiling situation. That means the vapor and liquid flowing together. Now, this is probably the most interesting one in terms of technological applications. Now, here I have the top line here. I have a straight pipe, which is heated along its periphery, along the boundary, it's heated. And then, of course, when you heat it, the boiling begins to happen. And then you can see the red gradually appearing along the boundary here. And the blue section is the liquid in there. Now you can see immediately the corresponding curved pipe situation, and below here, the curved pipe situation here. Now we have already got vapor in that, whereas in the straight pipe, you haven't got any vapor at the moment, very slight amount of vapor along the circumference. But you can see the boundary is mostly exposed to the cooler fluid, cooler liquid. The steam is hotter and the liquid is cooler on the boundary. And if you go to the next cross section, we are now gradually moving along the pipe to a new cross section. You can see more vapor has been produced in here, and more vapor, of course, has produced here. But the vapor, in the case of straight pipe, the vapor is surrounding the core of the liquid in the middle. Whereas here, the vapor is actually confined to the inner boundary, while the outer boundary is exposed to the heated wall. Heated wall is exposed to the liquid in the pipe. That means we have more opportunity to create vapor along that boundary rather than having vapor right around the boundary. So that's what you see as we progress in this passage. You can see now the vapor is here, much thicker layer, and we still have only liquid here, partial liquid, and the vapor is confined to the middle mostly. Now, what is the importance of this kind of observation? The vapor is like an insulating blanket around the liquid. So it prevents any heat going into the liquid further. So which means it actually affects the steam production rate. Whereas in a curved passage, the liquid is still in contact with the heated wall. That means you have more opportunity for the liquid to be converted into vapor more and more. So that is the advantage in this kind of operation. It creates a better opportunity to produce more and more liquid. The reason for that, the liquid is heavier compared to vapor. So liquid is always pushed to the outer wall and vapor to the inner wall, and therefore more liquid is always in contact with the heated pipe surface. Now that's a very important thing in design, this kind of a design, and that allows you to actually have a better efficiency in systems. Now let's see the animation. You can see how the boiling actually happens. The red is the vapor mass and the blue is the liquid mass. You can see the blanket effect around the heated surface is not there in curved passages. And because of that, you can produce steam in more effective manner in curved passages compared to straight passages. Now, I presented this in one of the conferences in Switzerland some time ago, and a lot of boiler manufacturers were thrilled to see this kind of a behavior, and they were nobody actually understood this phenomenon before, because this allows a massive amount of vapor production efficiency, very big jump in vapor production efficiency with very little wall superheat. Whereas in the case of a straight pipe, you've got to have a very large temperature difference between heated wall and the liquid to pump the heat from the surface to the fluid itself. Whereas here, you don't need that kind of a massive temperature difference to pump the heat into the liquid. So it is a very useful consideration for boiler design. So that is one of the key things came out of my research over the years in this kind of thing. And that's being cited quite well in industry and so on. Okay, so Professor, that's the end of that particular. Yes, sorry.
Sorry, just letting you know, we're just we are past our 1 hour mark, so just wanted to let you know.
Yeah, very quickly. It's only the last section now. So having done all the thermal work and all this modeling kind of things, our next step is to go into the more natural behaviors, especially the riverbed erosion or sedimentation kind of problems. So again, we started looking at that. One of my very good PhD students work on this particular problem, and he just got the PhD in February this year. And with all the difficulties we had with COVID, he managed to finish the work very, very well. So here we have a curved passage, as illustrated here. Now the bottom of this passage is filled with certain amount of granular material. It's like sand filled in there. Now sand density we can change. We can have different particle sizes and different grain sizes and so on. So we can actually recreate what's going to happen to the riverbed when it takes a turn in situations like this. And we developed a special technique to measure the profile. We use a laser pointers, special laser pointers, and we took coordinates along the cross section at different locations. Here I have shown only a couple of points, but we were able to get a lot of points here along the cross section as we progress through the flow problem. So as the flow passes through the channel, the profile of the bed will change as shown here. The profile will change. Initially it's flat, and then gradually due to the erosion happening due to the secondary flow, the bed will change. So we were able to look at that particular behavior. There's no heat transfer now. Simply the granular material is being picked up by the flow itself due to the secondary flow, secondary vortices, and then gets washed down the passage. And that's what we call the sedimentation. So we looked at sedimentation effect and erosion effect in curved passages. And this is applicable to slurry flows, especially in mining industry, when you have particles, sand particles or the particles mixed with the fluid, mixed with water, and when it's taking a turn, the fluid particles will come to the inner boundary, the solid particles get pushed to the outer boundary. Now that again creates a different kind of a erosion problem. The pipe walls get eroded due to the abrasive nature of these particles going with the fluid. So that is an important aspect in this kind of work as well. We haven't looked at that, but we looked at only the riverbed erosion kind of problems. So, and here, actually before that, I'll show you this again. Now here you can see in this diagram, we have marked certain boundaries like this. Now these boundaries are what we call the dunes. If you go to the riverbed, if the riverbed is dry, if river doesn't have water, you will see some sort of a pattern developing in there. Now that's what you call the dunes. So the dunes are developed because of the secondary flow action in that fluid. Now in my in our experiments, we were able to capture that in a video. And obviously in a thesis, we can't present the video in that manner. But here you have the option of seeing that kind of erosion. So this is the profile. That's going to be, this erosion happened due to the secondary flow motion in the passage. And then later you will see how it actually moves. So let's see the video. So there you can see the particles are being picked up by the secondary flow and gets washed down along the passage. You can see the dune formation in here. And then if you look at the entire passage, it's a long passage we had, very long passage, large curvature and so on. A lot of water, a lot of sand all over the lab floor when we were doing this experiment. A lot of leakages, you can see on the floor there, so much of leakage, and a lot of technical problems we had to resolve in doing this as well. And eventually somehow we managed to do this kind of work. It's a beautiful piece of work, and I'll show you that once again. And then you can see how the secondary flow is in action in here. And we have more advanced measurement techniques as well. We have the particle image velocimetry we can use. We can illuminate fluid flow with laser fluorescent particles, and then we can actually see the flow patterns as well. And so we are slowly developing more advanced techniques as well. So in addition to all these things, I'm doing a lot of other research in different areas. And this is my PhD work, essentially, the microwave evaporation, how the liquid evaporates in a boiling situation. You have a bubble, and how the liquid evaporates and produces vapor, and how the bubble shape changes, and how it leaves the heated surface. That was my PhD at that time. A very complex experiment. It looks simple here, but extremely complex experiment, because the life of a bubble is only less than a quarter of a second. So you got to have a very sophisticated way of observing various things, the temperature at the base, the evaporation, and all these things. Very complex. I'm not going to go into details of that. And another important, very interesting work I have done is actually called the pulse jet cooling mechanism. This is used for electronic cooling. So here we have a chamber with two diaphragms on either side, and the diaphragms oscillating with certain combination, and that will expel a jet of air through the orifice here, and that is directed to a cooling surface like this. This is like a CPU in a computer. Now this particular jet is not continuous. When the diaphragms are moving inwards, it will have the jet. When it's moving outwards, the jet stops. So this is an intermittent kind of a jet operation, which is a very, very powerful technique to cool electronic systems. We can use normal air. You don't need any liquid circuits or air circuits, because we draw the air from atmosphere and expel through the orifice again into the passage. So it's a very simple technique, and this is actually being well publicized in the past. I think about 2-3 years ago, we had a press interviews and all sorts of things when we first identified this particular behavior. It's a very effective technique for electronic cooling, and we have looked at how it's going to behave with the flow across that as well. We have a cross flow. It's like when the jet is coming down, we have another flow going across, disturbing this flow, how it's going to influence that. All this we have looked at in the past, and again, so many PhDs have come out of this kind of work as well. And then one of the other work I have done is called the microfluidics. That's a micro droplet formation. This is particularly useful in aeration problems or pharmaceutical industry, where we have to mix two fluids in a certain manner. And this top diagrams here shows a carrier fluid flowing across, picking up a different fluid at random in a certain frequency. And then you can actually keep mixing it with the fluid in a certain manner. So it's called the microfluidic behavior. Very, very tiny. This passage, the width of the passage is something like 0.5 of a millimeter. 0.5, very, very tiny. So that's why it's called the microfluidics. So I have looked at this kind of thing as well. Anyway, this is the summary of the work I have done all these years. And our research has significantly contributed to better understanding the secondary flow behavior and its implications. We have looked at the fluid flows, thermal behavior in curved ducts in great detail in different situations. We have come up with thermal optimization techniques, and we know how to interpret certain natural phenomena as well, like erosion and sedimentation. So, and we will be continuing this kind of work into the future if we have more opportunities as well with the PhD students and the grants and so on. And in conclusion, I especially want to thank the Institute of Engineers Sri Lanka and its WA chapter, and especially the 3 people who were involved with me all this time, Tissa, Anuradha, and also Asoka, who have actually sort of given me this opportunity and invited me to do this particular presentation. And also, most of all, I'd like to thank everyone for the participation as well. And thank you very much indeed. Okay, so that's the end of the presentation.
Thank you very much, Professor. Sorry, I just make sure. Yeah, I'm on mute. So now I would like to open the forum for any questions you might have from the audience. And Chamila, can you make sure that the unmute is switched off with all the participants? So we have a thank you message from Ahmed. Please feel free to unmute and say your messages.
May I ask a question?
Sure.
Fernando.
Yep.
Yeah, Tilak, thank you very much for a very nice presentation, and it's very insightful presentation. I thoroughly enjoyed it. I have a question. In your earlier slides, when you introduce Dean vortices, the direction you showed the direction of flow for those type of secondary flows. The direction of flow seems counterintuitive. Is there a reason for why those flows are the direction that you showed?
Yeah, I will go back to the beginning, very beginning.
It's one of the very early slides.
Yeah. So here you can see that that direction.
Yeah, that's that's the.
Okay,
the
so
red
this is
color,
like
is the red color the Dean's vortices, or no? Dean's vortices were
no. This is the no. This is the secondary flow. This is the secondary vortices.
Correct.
Now, yeah. So this is fairly obvious. I think
that's
the
obvious.
fluid.
That's intuitive.
Yeah, fluid is moving that direction.
Yeah.
And then it takes a turn due to the frictional effects. It comes back.
Yeah.
And then, if you look at the Dean vortices, it's definitely it's counterintuitive. The simple reason is that is the adverse pressure gradient. As you know, the fluid will have to have a negative pressure gradient to flow. That's the normal behavior. That means that if you have a pipe, the inlet of the pipe will have to have a higher pressure than outlet of the pipe. Then only the fluid will go in that direction. But now in this particular situation, you can see the fluid is being pushed against the boundary of outer boundary due to the centrifugal effects. Okay. So that actually creates what you call the adverse pressure gradient. It's the pressure against the fluid. It's like you are being pushed against. Say you are in a car, and the car is taking a turn, and then you are pushed against the door of the car.
Yeah.
And then there's a reaction from the door to keep you in position. So the same thing happens here. That reaction gives you a higher pressure at that boundary compared to this boundary. This is the lateral pressure, not the axial pressure direction. This is not from inlet to outlet. This is from inner boundary to the outer boundary. You have an increase in pressure.
Yeah.
So there are two pressure gradients here. One is the axial direction pressure gradient. The other one is the cross-sectional, we call it lateral pressure gradient. So that lateral pressure gradient is acting against the direction of the flow coming in. the pressure gradient, this pressure becomes more and more as we increase the flow rate. It becomes higher and higher. The magnitude becomes higher and higher. At one point, you find that the fluid actually comes to standstill at this point. It comes and hits the wall and it becomes stationary. And then since the fluid is feeling the pressure in the opposite direction, it begins to go in the other direction. Now this direction of the secondary, the Dean vortices, is determined by the frictional effect at that boundary, at this point here. Because this is like it's going this way, and this can only turn that way, opposite direction. So that is why it looks that's why it looks counterintuitive.
Yeah, thank you. I just have one more question.
Sure.
One of the key messages that came out in your presentation, when fluid flows through a curved path, it improves heat transfer. Now, is that an experimental observation, or can this be proven using thermodynamic laws and fluid mechanics?
Yes, certainly. It's you see, the thing is, what creates the heat transfer at a boundary? The heat transfer is created by the conduction effects first, and then it's taken over by convection. Convection means the fluid is free to move with that heat.
Right.
So initially the heat comes from the wall to the liquid. The liquid is actually stationary at the wall. That's what you call the static boundary. Mm-hmm. So the fluid is stationary, therefore you can only transfer heat by conduction, like a solid. And then once the heat comes into the sort of a middle of the fluid, or partly into the fluid is free to move. And therefore the fluid can actually take that heat and go somewhere else. That's called the convection. So what happens now, with the onset of Dean vortices, you are accentuating that process. You are accentuating the convection happening from the wall to the fluid. So there are two accentuating mechanisms here. The first one, of course, the main secondary vortex, which will pick up which will allow the mixing to happen more. And then later you find that the Dean vortices will kick in, and it will again also create a better or favorable mechanism to deliver that heat in a convective manner to the fluid. So it is actually a built-in mechanism. This is why the heat transfer improves. It's been shown experimentally as well as numerically.
That's very interesting. Thank you.
Okay, thank you. Okay, any other questions? I'm glad, I know Tyrone is an electrical engineer or electronic engineer.
Actually, this is not my field. My thermodynamics and fluid mechanics only goes as far as first year physics, and that was 30 years ago. But it was very interesting presentation.
Yeah. Actually, that is why I took up this particular piece of research. It was very appealing to me, and people haven't seen this before. They think, the bend is a bend. That's all. But actually, it does much more than just taking the fluid around the corner.
Yeah, very interesting.
Thank you.
Thank you, Tyrone. Any other questions?
Yeah, I have just a comment. Thank you very much for the informative presentation.
Sure.
And also, it's nice to see you there again. And and
sorry, is there any way we can see who's speaking?
I will switch on the.
No, Chamila is because I can't see the name even.
Yeah. Okay. I'm Ravindra here from Sydney, and
right.
I don't know how to switch on. I'll start the video.
Yeah, I may have.
Yeah. Anyway, it might take time, but yeah. My question is, we have. I have seen your those eddy currents at the river bends because that was our field then, and especially in studying river morphology, and that was very interesting. Currently, late last year we saw some people talking about self-compacting concrete and concrete being pumped to big bridge beams from one end to the other end. I always wondered how concrete is traveling without getting segregated to the other end of the beam, and and also when we pump concrete in long distances, concrete, once you mix it, it emits heat, it generates inside concrete. And yeah, you are doing those kinds of research.
I think my life is quite limited, in that sense. I've been looking at mostly the heat transfer type behavior, to be honest. And then lately I started looking at the river, the sand behavior, because my PhD student was very keen to get into that as well. But certainly, there are so many applications in mining industry, the maintaining the, what do you call this, the breakwaters kind of a thing in the sea, in the boundary of a sea or a river kind of a thing. We can look at all that. The thing is, they all have the same sort of principles. The principles wise is the same. So if it's open channel, the behavior we can study. I mean, it's a matter of getting into that, nothing else. But I haven't actually done that, except we looked at how the granular particles are being picked up by the fluid as it travels through a bend or some sort of a curvature. So that's all we have looked at.
Thank you very much, and that opens our eyes, and it's very interesting.
Yeah, thanks.
Thank you.
Yeah, but there is one interesting behavior that's actually the aberration of pumping systems, due to the particles in a fluid like a slurry. The slurry has a solid particles and liquid together traveling at the same time. So the solid particles get pushed to the outer boundary, and then it creates a more aberration or more wear and tear on the outside boundary than inside boundary in passages. Now that is a very critical problem which we haven't looked at yet, but we know we can do that as well. So that is one of the possible extensions of our work in the future.
Thank you so much.
Yeah.
Any more questions?
Yeah, hello, Anuradha, this is Nimal Jayaratna. I have put a
Nimal,
question. Hi, Tilak, it's a wonderful presentation. Thank you very much for that.
Yeah,
and I have a question for you. You did not, probably it's not important from your point of view, but surface roughness of the walls, how did you build that into your study?
Well, we are looking at, see, the surface roughness becomes important when you're looking at more microscopic kind of a level, actually. Now, in this kind of work, we are looking at more mechanism. I mean, I was looking at how the fluid is going to behave in a mechanistic manner within a curved passage, how it's going to improve the heat transfer process, how it's going to improve mixing. We were not looking at sort of a pressure drops, so to speak.
Oh, okay.
But the pressure drop, but the pressure drop, we accommodated to some extent in that one of the slides I showed earlier, the entropy calculation, the optimization problem, we looked at that in this particular slide. You can see here, we are looking at the black line is actually the viscous effects.
Yeah.
So we can actually calculate, but this is the viscous effect in the fluid itself, not very near the fluid wall, actually, not very near the wall of the passage. We are looking at the fluid element. Within the fluid, what is the development of viscous effects? So we were looking at that kind of a thing through the entropy calculation, the frictional effect contributing to the entropy in systems. So that's SP. So we went only up to that point, and we haven't looked at the really deep into the what do you call this the Darcy formula kind of a thing.
Okay, thank you.
All right, thank you.
Anyone else? I think if that's all the questions, maybe we can wrap it up. So I'd like to say a few thank yous, obviously, to Professor Chandra Tilaka, but I would also like to mention Chamila, who is from IESL parent body, for arranging the Zoom link and helping us with all the IT prep work. So that's greatly appreciated. And finally, thank you all to the audience. Thank you for joining us in our first presentation. And please, if you have any follow-up questions or any comments or ideas on how to better improve our presentation or any feedback, most welcome. I will put the email address on the chat box. Yeah, that concludes our event for the evening.
Yeah, Anuradha, I have before you go, I have one little suggestion.
Yeah.
First of all, I just want to know whether animation was seen well through the system. Did you see the animation?
I saw the animation at a slower rate, like it was a bit.
Okay.
Yeah, but I could see the animation. Anybody else have any comments on the animation?
Same thing.
Did everyone else
animation and the presentation could be seen well, but of course it went slightly slowly.
Slowly, but not breaking or anything.
No.
It was quite okay. Yeah. The suggestion I could make is a lot of participants have been waiting at the beginning, so it's better to have some kind of an opening slide on the platform.
Yes.
Before you do anything, otherwise it looks little.
That's
we don't
right.
know what to do. It's like waiting in an airport lounge, to get into the plane.
That's a good point.
Yeah, it's good to have that kind of a
starting slide and
something
like previous.
Yeah, and you can also have a countdown kind of a counter showing how much time we have in the for the presentation next. I think that's the kind of a thing we can do to improve it.
Yep. Thank you.
All right.
That's very
anyway, I'd like to thank Shamila as well. I forgot to mention his name earlier, and so Shamila is very helpful actually initially setting up everything and going through the motions. Thanks to all of you, and so we'll catch up some other time again.
Most certainly, yes. Thank you, Tilak, and thank you, Shamila. And adios from Perth.
Yeah. I will be just putting the email address on the chat box.
Yeah.
Okay.
Thank you.
Okay then. Thanks very much indeed.
Thank you.